Okay, I saved the best for the end. Reverse engineering the cache can be fun. So in such problems, you're typically given not the entire cache configuration, but some parts of it. And then you would be given a sequence of addressees and their hits and misses. So it's as if someone took a sequence of addressees, wrote a cache simulator, figured out what the hits and misses are, and they are not giving you the exact cache configuration, and you're asked to figure out what the configuration should be. So the address pattern and the hit and misses typically have enough constraints so that you can figure out the rest of the parameters. So the key is to really come up with those constraints, and from those constraints you can derive the cache parameters. So let's see how we can go about deriving those constraints for this problem. So we're given the cache size to be of 512 bytes, and the address is 12 bits and nothing else. We have to figure out the block size, associativity, and the number of sets, all from this data that we are given here. Okay, let's see how to go about figuring out the block size first. So let's now look at the first few cache accesses. So you'll notice that the first 3 out of 4 accesses, they all have the same prefix to their address. Maybe they all came from the same block, and if they did, then maybe we could conclude something about the block size. We also see that couple of them were misses, and the third one was a hit. So maybe the miss, the second axis being a miss, can tell us something about how what is the largest size possible for a block, because if the block was really big, then given that the prefix were somewhat the same, it would have been a hit if you were able to exploit spatial locality. So that should give us an upper bound on what the cache block size should be. And the second axis, or sorry, the third axis is a hit, and this address was not accessed before. So that means you're exploiting spatial locality. So this should give us a bound on what is the smallest possible block size. So between those two constraints, maybe we could figure out what the block size should be. Okay, so now let's start off by converting these 3 addresses to the binary format. So the given address is in hexadecimal, obviously. So you have so I've converted the 3 addresses to the binary format, and we know that this address is a miss, this address is a miss, and this one is a hit. Now you will notice that the prefix for the first 2 addresses are the same, except until this point. After that they diverge. So given that the second axis is a miss, it clearly means that the second address is not part of the same block as the first address. Now if I had chosen let's say a block of size 2 to the power of 5, meaning my block offset is 5 bits, and then I would draw the partition here and say, well, my tag is going to be whatever it is to the left, and you will notice that the tag is exactly the same. So if the tags are same, then I would have observed a cache hit because they are next to each other. Clearly they are not part of the same block, which means they should have different tags, which means clearly the block size has to be smaller than 2 to the power of 5. Perhaps the block size cannot be bigger than 2 to the power of 4. So from just these 2 accesses I can infer that the block size should be less than or equal to 2 to the power of 4. So now let's see if I can derive one more constraint. If I look at the third axis, that turned out to be a hit. Third meaning I'm not worried about this one in the middle. I'm just considering 1, 2, and 3 here. So the third axis here is a hit, and which means that it must be part of the same block as one of the previous two addressees. Now the question is, which one could it be part of? Well, we need to see which one it shares the longest prefix with. It turns out that it shares the longest prefix with the first address, and so maybe it is part of that first block. And that means what if you draw the boundary over here and say my 4 bits is my block offset, and you will see that the block offset cannot be any smaller than 4 bits, because if I draw a line with just 3 block offset, then you will see that the prefix doesn't really match, which means the tag doesn't really match with any of the previous two accessees. So given that this is a hit, this is clearly not possible. So therefore it has to be, the block has to be at least as big as 2 to the power 4. So now if you combine these two constraints, then you will get the block size to be 2 to the power 4, which is 16 bytes. So once you figure out what the block size should be, then we can compute the total number of blocks very easily. So that is 2 to the power of 9 divided by 2 to the power of 4. So that is 32 lines. So your cache has 32 lines. So 512 byte cache, because each block size is 16 bytes, you have 32 lines. So now let's figure out what should be the associativity of this cache. So we know that in addition to 512 byte cache size, each block is of size 16 bytes. Now to figure out the associativity, again, there is no standard procedure that you could use, but one strategy could be that you try the direct mapped cache, see if the direct mapped cache is consistent with the hit miss pattern that is given to you. If not, try 2-way, then if not, try 4-way, and see if you can find contradiction for any one of those designs. The moment you find a contradiction, then you can discard it. So you don't have to simulate for all the addressees, you just need to simulate enough to discover a contradiction. And when there is a contradiction, you know that it's not the right solution. So now let's try the direct mapped cache and see if it would work. So for a direct mapped cache, we have to figure out the set index and the tag. So we know that the block offset is going to be 4 bits. And we also know that the number of cache lines is 32. So we have 32 cache lines in a direct mapped cache, which means log to the 32 number of set index, so that will be 5 bits, and the remaining will be tag, so it's a 12-bit address, so that will be 3 bits for the tag. Okay, so now I can try to simulate my cache for the direct mapped cache with this information. So it's worthwhile to compute my set index for tag and set index for these addressees. So that this would be 0, 0. So I have converted the addressees into binary form, but I have not translated the last nibble, because I know that the last 4-bit is a block offset, and the block offset doesn't really affect my cache hit or miss rate. So I have only translated the first 2 bits, first 2 nibbles. So this would be this, and this would be this, and that's enough for me to figure out my tag and set index. So my set index has 5 bits in it, so these would be the set index, and the first 3 bits would be the tag. So now let me simulate my direct mapped cache. So I will see that, you'll see that the first one, the set index is 10001, so that is And you'll also notice that the third address has the same set index as the first address, and the fourth one also has the same address. So now if it was a direct mapped cache, then these two addresses would map to the same set index, which is 1001, right, which is really 17. So if this was a direct mapped cache, then you can conclude that because of the fact that this address will map to the same set as this address, it would have evicted this address, and so therefore let's simulate this cache and see what will happen. So I have the tag 1 after executing the first instruction. I'm not going to bother about this one for now because it has a different set index, and this index has a tag of 2, so this would have evicted it, so it will be 2 0 1 0. And then for this axis, again the set index is same, but the tag is 1, which I had evicted, so it would be a cache miss. So if I use a direct mapped cache, this axis would be a cache miss, and that's a contradiction. So therefore I can rule out that my cache is not a direct mapped cache. So I now need to try out a two-way set associative cache. So in the case of a two-way set associative cache, I would not have 32 sets. I would have half of that, so that will be 16, which means that my set index would be just 4 bits, which would kind of makes it easier to know what the set index is, because this is going to be my set index. So given that is my set index, let's see if I can simulate my entire address pattern and make sure that it is consistent with the cache configuration that I'm discovering. Okay, so again I have written just the first and the second nibble. I've ignored the block offset when I translate it into the binary, because the block offset doesn't really help me simulate my cache. All right, so my set index is defined by my the nibble in the middle. So I would have set index 1, it has a tag 3, and then set index 0, tag 3 again, so both of them are misses. So far we are good. And then we have a set index 1, tag 5, so the set index 1 would map to the same set, but however it's a two-way set associative cache, so I have 2 cache blocks per set, so that means I have another cache line that maps to the set 1, so I can store this tag 5 in the second way. And then if I simulate my next address, it will map to the same index, and I will notice that it is actually a cache hit. Great, it's consistent. Now my address 72D, it will map to index 2 with the tag 7, and then 72F, which will also map to the same index, same tag, so that will be a hit, and it is consistent. And then I have set index 2, tag 3, set index 2, tag 3, I don't have it, so it has a miss. Set index 2, tag 5, again this is a miss. So so this means I have to evict a cache block. I have to evict the least recently used cache block from the set 2. We just finished accessing the tag 3, so address 7 is the least recently used, so I'll have to evict that, and I replace it with the new tag 5, and then I finally access the last address, which is also set index 2 and 7, which we just happen to evict. So it turns out to be a miss. Again, it's consistent. So we just finished simulating a two-way set associative cache, and it seems to work well. There is no contradiction at all. So we can conclude that this cache configuration is a valid configuration for the given problem. Now, just for fun, we may want to double check and make sure that we got it right. And if we got it right, then higher associativity should result in contradiction. So after two-way set associative cache, we can try four-way set associative cache. So if we were to try four-way set associative cache, we can see if any one of the misses would have turned into a hit. And as we were going through this exercise, you would have noticed that this cache block at the end, we had accessed it before, right? And so it would have been a hit if not for this conflict that we had between the tags 5 and 7. And so if I had a four-way set associative or a three-way set associative even, then it's quite possible that it's possible that 7 and 5 can both be stored at the same time. And so you can go through this exercise and figure it out by yourself. You'll see that in a four-way set associative cache, this access would turn out to be a hit, and that would be a contradiction. So from that exercise, we can get more confidence that the given problem, the cache in the given problem has is two-way set associativity. So we figured out that it's a block size is 16 bytes and set associativity is two-way. And given that information, then we can figure out the number of sets. That is simply the 16 sets, because we have 32 lines.